Alrighty, ladies and gentlemen, we're going to talk about the final nitrogenous nucleophile for the evening, and that is going to be the formation of the enamine, which structurally looks like this. Now, unlike the imine, there is a little bit of sense with this name because En, you typically think of C double bond C bonds, and amine, you should probably think of nitrogen. And as you can see from our structure, we've got the C double bond C bond right there, and the nitrogen group up there. So these are formed from the reaction of a carbonyl. Just for grins, I am going to go with a very poorly drawn cyclopentanol. Excuse me, cyclopentanone. Ooh, I got tripped up on my own nomenclature. And we are going to react this with a secondary amine. Now, our secondary amine looks like this. I'm not exactly sure, I don't clearly remember the name of it. I apologize for that. But we're going to go with this. Remember, a secondary amine is any nitrogen that has two different carbon groups on it. And we're going to do this in trace acid. And the product will look like this. If you're wondering if I have a thing for pentagrams, you're right. I've been tracing them all day in my basement, trying to summon up something that could let us all go back to school and work, but it hasn't performed yet. So this is the enamine. Now, how this works, it actually greatly resembles the mechanism of the imine formation. So to start with, what we're going to do is take our slightly better drawn cyclopentanone, and we're going to deprotonate it off of the hydronium. Acid-catalyzed pathways, these tend to give you equilibrium processes. So now we're here. Remember, the protonated carbonyl is the primed pump. It makes the carbonyl carbon more susceptible to reaction. So the reaction itself comes from the nucleophilic attack onto the carbon, breaks open the carbon-oxygen pi bond, which quenches out the positive charge on the oxygen. So equilibrium-wise, now we're here. Now this is where I really regret giving you such a complicated ketone to start with, because I don't know what just happened there. I apologize. Something weird happened on my computer. Now we don't have that at all. So let's try me doing this, not screwing it up. We've got this. Intramolecular deprotonation. We pull the proton off with this OH. The electrons stay behind and quench out the nitrogen. And now we're here. Now, in case you're wondering, if this were an imine or a primary amine, this would be when the pi bond forms, knocks off the water. But problem is, if you go back and rewatch the imine video, which I invite you to do, go ahead, I'll wait. All right, hey, you're back. That's good. You'll notice that when you do the imine video, you'll use the lone pair of electrons to slam down, and then you can deprotonate it at the other side. We don't have that liberty here because there are now 2 carbon groups on that nitrogen. This is not going to want to slam home the carbon-nitrogen pi bond that you want. So instead, this is what happens. The water, again, where did this water come from? Probably up here off of the hydronium to start with. Water deprotonates the carbon, electrons slam down, we knock off the OH2. So this gives you something that you would call an enamine. Look, works like that. Now, the exact reason we make enamines we're going to have to deal with in a couple chapters. It has something to do with a conjugate addition through the pi bond. These are slightly trickier to make than imines because, unlike the imine, your enamine tends to want to stay in solution. So you've got to find other ways of separating them out. I am going to pose this puzzle to you, though, and I'm not going to give you the answer until the next video. I want you to logic if we had this reaction. And we're going to react the cyclohexanone there with dimethylamine and trace acid. What you'll notice here is, unlike our previous example, the 2 carbons are not symmetrical. Let me show you what I mean. Over here on cyclopentanone, that carbon and that carbon were structurally identical. But here on this methyl cyclohexanone, the carbons are fundamentally... I'm waiting as my computer decides to screw me over here. The carbons are different. This has turned into a disaster, folks. I'm now learning that I'm not very good with technology. So there are 2 separate carbons there, which means there are 2 products. Neither one of them look like that. And I can't find the eraser tool. Oh, there it is. Whee! Okay, so your products would look like this. Or this. What I want you guys to figure out for me is, which one of these 2 do you think will be the major organic product? I want you to think this through, and what I want you to do is answer it in the comments section below. So your options will be, this is product A, and this would be product B. So I want you to sit and work on this, figure it out, and then answer it in the comment section on this video. And then what I'll do is I'll make another short video answering the question and explaining to you why, and then we'll go on to a few more carbon nucleophiles, including a reaction that you're going to look at and go, he's just making this shit up now, isn't he? He's just making this crap up. All right, everyone have a good night, and I will have more videos for you tomorrow.